All right, folks, we are going to get into some numerical integration with trapezoid rule and Simpson's rule. This is going to be the first half of your notes. The other half I made last year, so if I say stuff like, sorry I can't be there, it's probably because I made it when I was out last year for some reason. So you can ignore that part of it. But we're going to get through up until basically the error section. So eventually we'll do a little quiz on 4, 5, 4, 6, but this is going to be another way to approximate the area. A trapezoid is a little bit more accurate than what we were using like with the rectangles before, but it's a very similar idea, so it's going to feel kind of like what we did last class. Simpson's rule is also going to be more accurate, but it uses different functions, so it's even more accurate than the trapezoid rule. So we're kind of going backwards a little bit with the idea that you can find area with other shapes, but it's a pretty quick part of the unit. So just a reminder of what the formula is for the area of a trapezoid. It is 1/2 your height times base 1 plus base 2. So if you're looking at the height of your function, they'll usually give it to you, but there's also going to be kind of a shortcut rule to help you figure it out. But I'm going to show you how it's going to look. Just a reminder that this would be like base 1, this is base 2, and then your height would actually be, weirdly enough, this part. So that's what we're going to go with in our formula. All right, so as I've done before, I'm going to show you where this formula comes from. So if we actually created trapezoids out of this figure, you can actually make one giant trapezoid and just cut it into sections. So that's what I'm going to do. I'm going to go from this point A to this point B, literally make a trapezoid out of that, and then cut it into the little segments that they're trying to give us. Hopefully you can draw lines better than I can, because that was terrible. Anyway, what you should notice is that your base 1 would be here, your base 2 is here for your first trapezoid. Then, this is we're used to as delta x, but that's actually the same thing as h, okay? So the formula is literally going to be 1/2 delta x, because that's your height, times your base 1 plus your base 2. The problem is that base 1, we don't know the length of, so as per usual, how could you figure out that height? That's right, take f of a. How could you figure out the height of base 2? That's right, f of a plus delta x, as we're used to doing. So what it ends up looking like is you figure out the area of one of them, so it's 1/2 delta x times f of a plus f of a plus delta x, and so on. So you have to add 1/2 delta x times f of a plus x, a plus delta x, because that's literally now your base 1 for your second rectangle. So if you add that delta x, now we need to do delta f of a plus 2 delta x's for that second one. So if you're looking at that second trapezoid, this is the second one. Base 1 is actually now the base 2 from the previous one. And then base 2 is a plus 2 delta x's, because notice again, or I'll highlight in a different color, you have 2 delta x's added on. So if you keep adding all of those different rectangles, what happens is it creates a pattern where you're going to see repeats. Basically what that means is the first one is by itself, right? F of the initial part, f of a, is by itself. you're going to have overlap between each of these middle ones. Because notice again, this repeated itself. It was base 2 here, but it became base 1 there. And then the last one obviously is going to be by itself as well. It would be like f of b, if that makes more sense. So this is almost like f of a. This is like f of b, okay? This is your height. It's actually delta x that we're used to seeing. So if you forgot that part, it's like b minus a over n, like we're used to doing. It just has the 1/2 in front because the formula is 1/2 height times base 1 plus base 2. So let's see this formula in action. Okay. So use the trapezoid rule to approximate. You guys know that if you actually integrated this, it comes out to, so the integral of sine is negative cosine, and then you could plug in pi and 0. Just a reminder that the actual answer for this, because we've actually done this question before, is 2. So you're going to see how close the trapezoid and Simpson's rule come. Simpson's rule obviously is going to be more accurate, but for now, what we can do is just plug in the formula. So we're going to start with n equals 4. What that means is you would have 4 trapezoids. So all that does is it changes what you're plugging into the formula and like what values to see. So I'm going to do it out for you so you can see it. But we're still going to do b minus a over n, or you can do 1/2 b minus a over n. They write it as 2 times n, and our n is 4 in this case. But just remember that's the same thing as 1/2 times your height, which is b minus a over n, which we're used to seeing for delta x. So this is just kind of like a shortcut for you. All right, so we want to do the first value. So we're starting at 0 and going to pi. If you need to visualize it, these are the values, 0 and pi. We want 4 trapezoids between those. 1, 2, 3, 4. So that means I'm going to start with f of 0, right, as the formula said. Just a reminder that if we put this value here, this is going to be pi over 4. Because if I divide pi by 4, hence 4, you get that. This is pi over 2, and this is 3 pi over 4. Okay, so that kind of helps me figure out what I'm plugging in. So I'm going to do f of 0. I have to do 2 f of pi over 4s, because remember, this is going to be base 2 for the first trapezoid, but base 1 for the second trapezoid, hence why they double. So all the middle numbers are going to be doubled. So then I have to do 2 times f of pi over 2. I'm going to go down a little bit, plus 2 times f of pi, 3 pi over 4. And then plus f of pi. Remember, f of pi is by itself because that's only the base 2 in that last trapezoid, basically. So the pattern is 1, 2, 2, 2. All the middle ones are 2s, and then the last one is 1 as well. So then all you have to do is simplify this. So you end up with pi over 8 times, and then evaluate. So if I plug in 0 for sine of x, I end up with 0. If I plug in pi over 4 for sine of x, that's pi over 2, but times 2 is just going to be radical 2. 2 times, again, pi over 3, 3 pi over 4, or sorry, I missed pi over 2. So pi over 2, if I look for the sine of pi over 2, that is 1, but I have to multiply by 2, so it's 2. And then 3 pi over 4 has the same sine value, so it's going to be radical 2. And then the sine of pi is 0. Okay, so you add those all up, excuse me, and you get pi over 8 times 2 plus 2 radical 2, which is 1.896. So fairly close to the actual answer, the area under sine, which is 2, but a little bit off. Notice what happens when you have n equals 8. See if you can figure this one out. Just a reminder that this number will change, and then you're going to have more values in between. So if you need to draw a number line for yourself to help yourself split it into eighths, please feel free. Or you can just literally think about what's happening to each of those increments. So pause the video, try it out, and when you're done, you'll see the answer. All right, so hopefully you got what I got, which was 1.97. Obviously, like 3 pi over 8 is not on your unit circle, so you guys can just plug that whole thing into your graphing calculator. Just make sure you're in radians if you're using your calculator to plug in. Notice that my back is still a little sore. Notice that we went up by pi over 8s, because you're literally taking that whole increment and dividing it into eighths. So if you didn't realize that before, that's what happened, and hopefully you remember from the previous unit that the more shapes you create underneath the curve, the more accurate it's going to be. So notice we're super close to 2 again, okay? So Simpson's rule is going to be even better, because what it literally does is it creates 2 different shapes within a function that help you approximate the area under each part. So what that'll look like, you can flip to, they're saying that you can literally sketch a parabola into a function and find the area underneath, and then draw another parabola and find the area underneath that one. So again, because of the way that this works, you're going to have the same point representing 4 different times, or 3 different times, or 2 different times. So next page, if you're following along on paper. But notice that you're going to have things split up into slightly different segments. So based off of the shapes that they create, this is a slightly different version, but it's basically creating like a quadratic in between each curve. So if you go back, that's why the pattern ends up being 1, 4, 2, 4, 2, 4. So it just literally alternates depending on how many values you have. The number of intervals is always going to be an even number, just so you know, but we're now dividing by 3 because it ends up creating, when we think about a parabola, it has 3 points of connection. That's really why that works. All right, so we are going to use it in action. Visually, it's a little bit harder to see how that one works, but I want you to see how much closer this one's going to be to the real answer. Just a reminder that we're doing the same function, so this would be 2 is the actual. But now we're going to use Simpson's rule, which means you get even closer with the approximation of the area. So if we start with n equals 4, we're just going to plug into that formula. So we have b minus a, our b is pi, our a is 0 still, over 3 times n. The nice thing about the assessment for this is you guys can use the formulas, so you don't have to memorize anything. So you can have them in front of you. Then we do f of 0 plus 4f of our first coordinate, which if you look back at the previous page, we did this already, so that's how I know it's pi over 4. Notice that it changes to a 2, so it alternates. And then 4 again. And then we're done with the repeats, so I have just plus f of pi is my last one. If you plug that into your calculator, or if you want to do it out by hand, that's okay. It ends up literally being 2.00, so it's like super close. And then, if you do it with n equals 8, I want you to try this one. You have all the f of whatever values you have from the previous question. Hopefully, you can just look back at it. But try this for n equals 8 and see how much closer you even get to. Technically, 2.00 is very close, but you'll see something slightly different on the next one. All right, hopefully you did exactly what I did and got even closer. You get 2.000. So it's not perfect because the exact way to do it is just take the integral like we have been doing. But these, hopefully you can see, are even closer than what we were doing before with rectangles. Okay, this is our last set of questions. I'm going to have you try on the next page. So what it does is it asks you to use Simpson's rule, sorry, the trapezoid rule, Simpson's rule, and then the fundamental theorem of calculus to find the area. The fundamental theorem of calculus, remember, is literally just take the integral. They're all for the same n values, so you don't have to know like all the different x values to plug in, which is kind of nice. Just be careful, you're going from 1 to 3, and you have to split that up into fourths, which means you are going up by a half, if you didn't realize that. The shortcut to figure out how you're going up by is literally it's delta x, which remember delta x is b minus a over n. So if you ever need a reminder of that, that's a b. So if you're going between 1 and 3, which is what they're having you evaluate for, if you split it up, that ends up being you're going up by a half. So it's nice you don't have to do that twice, because they don't change the n value on you for each. So I'm going to have you try this completely on your own. We'll do the last one together just for ease and time. But I'm going to have you figure out the trap equation answer, the Simpson's rule, and then the fundamental theorem. Fundamental is literally just integrating how we usually do. So no need for u substitution, literally just integrate that. And they should all come out pretty close, but remember Simpson's is going to be the closest. So pause the video, try it out, and hopefully get close to the correct answer for the trap instance. All right, so hopefully you got for trap negative 0.75, which is close to the actual answer. Just a reminder that that's negative 2/3. If you need a quick refresher on integration, that's what you do for the fundamental theorem of calculus, and then you end up with negative 2/3 when you do Simpsons. So it's like super close to the actual. All right, the last one we're going to set up together, and then you'll see how it works. So you want to do trap, Simpsons, and I know 8 is a lot to write out, but a quiz or test, I want you to actually do that. And then the fundamental theorem, just for funsies. Let's start with the fundamental theorem because we know that that one's super nice. So you're going from 0 to 8, x to the 1/3 dx. So if you integrate that, you end up with x to the 4/3 times 3/4 between 0 and 8. So literally, if you plug in 0, you get 0 back, so you really only have to do this for the 8. So you get 3/4 times 8 to the 4/3, which is really 2 to the 4th, because the cube root of 8 is 2, times 3/4. So you get 3/4 times 16, which is 12. We'll see how close we get. So for trapezoid, we got to do 8, because 8 minus 0, over 2 times 8, because that's n, times f of 0 plus 2f of 1. The nice thing about it being split into eighths between 0 and 8 is it's literally going up by 1, which is so nice. Plus 2f of 2. I'm going to have you do a little dot, dot, dot here because you can plug it into your calculator. And then we'll do 2f of 7 plus f of 8. Remember, the 8 is by itself because that's like the last base of your trapezoid. So if you plug that all in, I'm actually going to have you try that. Plug it all in, get an answer in your calc, and then unpause the video. All right, hopefully you got, technically this should be approximate, but 11.73. So fairly close to 2, but you'll see Simpsons does a better job. So we're going to do 8 again, because it's 8 minus 0, over, be careful, it changes to 3 times 8. And then we're going to do, again, f of 0 plus 4f of 1, so be careful here, plus 2f of 2. Just a reminder that it alternates, so if you do the dot, 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 you got to just be careful that in your calculator you're plugging in correctly. So it goes 2 times f of 2, 4 times f of 3, 2 times f of 4, 4 times f of 5, 2 times f of 6, 4 times f of 7, because I think it's like symmetric, and then f of 8 by itself again, okay? Plug that into your calc again, and hopefully you'll see it gets closer to 12. All right, so not quite as good as the last, not the question, this last one, but the one before we had like almost exactly the right answer. So anyway, hopefully you are having a good week. Please reach out, come to my office hours if you have trouble. Just a reminder that part 2 will show up tomorrow, but I made it last year, so if there's anything weird that I say, it's because I made it last year. So I mentioned probably that I am not able to be with you guys because I'm homesick or something, and I don't know why. But either way, no, it's still good to go. So if you have questions, let me know. Have a great day.